quick overview. I want to highlight again about NXP's ARM Continuum stuff. Talk about the portfolio as an overview to start teasing the presentation a little bit. And then starting with what we have today, which is the LPC11100. I'm going to talk about what we're going to do in 2011. And then I started reviewing all the trade secrets. There's a new part that we're going to announce soon, actually, before Christmas, the LPC1200 family. And then finally, actually, that's going to be the meat of the presentation, which is I'm going to talk about a few of the key and the cool IPs that we have thought about we're going to integrate, most likely happening in 2011. So that's basically the agenda. So let me go back to this microcontroller landscape, right? Some of you who's familiar with NXP microcontrollers probably have seen this slide before, and we actually talk about it in the last session. So traditionally, people look at the landscape and people categorize it as 8-bit, 16-bit, 32-bit. We segment this microcontroller market in a certain way, and people think about 8-bits low cost, low performance, 32-bits high cost and higher performance. Well, it's not necessarily true anymore, right? So if you look at the ARM offering, of course they came out with the M3 first, but the Cortex-M0 was designed exclusively for targeting the 8-bit and the 16-bit market applications. So at NXP, we look at this landscape differently. We 100% ARM focused. So we have the Cortex-M0, M3, M4, and the fact is, again, Cortex-M0 is so much targeting the 8-bit and 16-bit applications. We look at this continuum as a trend, not segmenting our customers or the market based on 16-bit and 32-bit. And the most beautiful thing about this, our view is our Cortex-M family devices are actually binary and 2 compatible. So for customers, there's a much easier leverage in terms of scale that you design. You can start with something basic, and later on you want something upgraded, adding more features, adding more competition capabilities. You can easily moving from M0 to M3, and easily moving from M3 to M4, adding a lot of the arithmetic calculation capabilities. So again, I said we are 100% ARM focused. We actually is the only vendor has microcontrollers that's offering with all the ARM cores, with ARM 7, ARM 9, and now of course all the Cortex-M0 portfolio. So now you look at it from an application standpoint. In the low end you have the microcontroller. In the mid end you have data signal control stuff, and then on the upper end we have the application processor. We very much focus on the left bottom side of that things, which is microcontroller. Of course, the Cortex-M4 bring us to the digital signal control or digital signal processing arena, and we actually believe that's going to be a very successful part moving forward. And some of you who are interested about this, check out our news announcements. So let me move forward, go back to talk about the LPC11100. So we announced this part at the end of 2009, okay? So that's not something new, right? But then I want to start my presentation from there. So again, the Cortex-M0 was ARM's smallest, lowest cost, lowest energy, most energy efficient core ever. And it has a lot of promises. And at NXP, we claim to customers, you have 2 to 10 times performance improvements against the traditional or some of the legacy 8-bit microcontrollers. We offer smaller and higher code density or smaller code size. We offer even power savings. I'm going to show you some of the slides later why, as a marketing person, I'm willing to make these kind of bold claims. But the point here is, you started with a very nice core, and what we're going to do about this, right? So let's look at the core first. If you compare, again, go back to what I said earlier, we don't look at the things with 8-bit and 16-bit, 32-bit anymore. And the big reason is that even if you look at the 8-bit microcontrollers, it doesn't necessarily only use 8-bit instructions, right? So the familiar 8051, yes, majority of the instructions is 8-bit, but it goes as high as 16-bit. And even if you look at the famous MFC 430, the instruction set varies also. Now for the Cortex-M0 though, and I apologize for the people at the back, but if you look at this chart on the left and top corner, where the white section is where the Cortex-M0 instruction set is. Everything you see is actually 16-bit, not 32-bit. There's only one exception right there, but everything else, all the instructions for this Cortex-M0 core is 16-bit based. So, what's the benefit of this, right? If you use an 8-bit microcontroller, and if your code size go up to above 64K, you have to use the concept of operands. You have to do pagings, right? You have to manage your memories and code. And that's actually introducing the programming overheads, basically. So you add a lot of complexity for software developers, for the embedded firmware engineers to manage your code. And we believe the Cortex-M0 offers huge benefit from that perspective, because we have 16-bit wide instructions, but we have a lot of address space available, virtually unlimited for the firmware development for your application. So you don't have to worry about all the overheads. So what's the benefit of this comparison? Is, I want to introduce you to this concept of CoreMark, right? What is CoreMark? Why do we use CoreMark? So CoreMark is actually an independent benchmark that measures the CPU performance for 8-bit and 16-bit CPUs. So the point here is, we say, okay, we want to sell the Cortex-M0 into the 8-bit and 16-bit market. So we have to use the benchmark that people use for measuring the performance of 8-bit and 16-bit microcontrollers. So if you run the instruction set that's designed by CoreMark, and by the way, you can download their program by yourself. Just go to their website here, coremark.org. Download the program, you can measure the scores, right? So what you compare here is code size comparison. Like I said earlier, when you're doing the paging or the programming overhead, you don't really enjoy a lot of the benefit from the code density. So if you compare versus some of the typical 8-bit and 16-bit microcontroller in the market, you actually see the benefit that Cortex-M families enjoy much higher code density and smaller code size. What does that mean? Smaller flash and, of course, lower system cost. And let me give you another example. This is actually a famous table showed by ARM. Also, this is a simple 16-bit multiply instruction. With the Cortex-M0, you can get the 16-bit multiply finished in one clock cycle. That's one single piece of instruction. Very simple and clean. And this is an example using MSP 430. You will need 8 cycles. Actually, that's 4 instructions, and then takes about 8 bytes. Now, if you look at the traditional 8051 approach, though, it will take 28 instructions, 48 clock cycles. So now you can see here, though, the point here is, although you may think of the 8051, the 8-bit microcontroller, will have a relatively lower active power, but it will have to stay in the active mode for a longer period of time because it takes more clock cycles to execute a certain amount, given the amount of computations. And I don't think I'm using a very extreme case here. I think in a lot of the application today, it's almost unavoidable. You have to deal with a lot of data processing. It's not uncommon that the 8-bit microcontrollers today will have, say, a 12-bit ADC, 10-bit ADC. You have to do some, serial communication, data manipulation, and then spit it out to your system. So the point here is, with more and more arithmetic calculations, you start seeing that the 8-bit and 16-bit microcontrollers no longer be able to fulfill this task easily and efficiently. So this is going back to the point I said earlier. So if you look at the active mode, right, the 8-bit and 16-bit microcontrollers will have to stay in the active mode longer. So overall, where's the power? The active current number really doesn't matter. So when it comes to power measurements, you have to think about the time domains. So the ARM Cortex-M0 core really actually show the efficiency in terms of power consumptions compared with the traditional designs. Again, this is the CoreMark numbers. We got it from this independent website, so feel free to check it out. So let me go back to my earlier LPC11100 discussion. And I said we launched this part in the end of 2009. So what's new about this part? Well, has a Cortex-M0 core, go up to 50 megahertz. It's a simple, small microcontroller, again, targeted the 8-bit and 16-bit applications. So it has up to 32K of flash, which is again very typical. But one thing I want to highlight here, besides all of the basic peripherals that you commonly found from 8-bit microcontrollers, is we actually reduced the power, the active current of this device from 150 down to 130 just recently. So this is actually the trend moving forward. We introduced the LPC111L family, and L stands for low power. But that's the key, right? So active mode, we bring down the number from 150 down to 130. That's over 15% of reduction. In the deep sleep mode, we actually lowered it by threefold, down from 6 microamp to 2. That's even better. And then we actually remain the same for the deep power down mode. But one thing I do want to highlight here, though, is for the NXP microcontrollers, the M0 families, we actually have 5 programmable registers that you can do data retention. So basically, not everything, but some of the critical data you dump into the registers before the CPU falls asleep. So when you wake up, it helps you to find out what happened before you went down to deep power down mode. So what is our trend, though? But if you're comparing some of the key players in the market, right? I wouldn't say New Wotan yet, but I think TI, Atmel, SD Micro are very strong competitors in this market too, and respectable companies. And you look at their product portfolios, NXP still have the lowest active current at this moment, with 130. And we of course we're not going to stand still. So moving forward, I think in 2011. Our target is bring down this to 100 microamp. That's basically our goal. So we actually have full confidence that's going to happen, and this is where we're going to move forward in the next year. The other thing that's cool about this 1100 series, we actually have one part that's actually the smallest 32-bit ARM MCU in the world. It only measures 2 by 2. So you say, wow, that's tiny, right? That is tiny. And the good thing about it is a lot of customers want to do, say, wireless sensors or home entertainment controls or anything that's around you, but you don't want to see it, but it's hidden there that helps you to control certain things, the sensor applications. You want your microcontroller to be as small as possible.
What package comes in?
This is a CSP, chip scale package. Wafer level chip scale package. So 2 by 2, tiny, right? But just because it's small doesn't mean it's underpowered. It has a complete ADC, has a SPI, all your serial interface, has up to 32K of flash. So it's a complete microcontroller in a very tiny package. We're the smallest, and also still enjoy the lowest active power. We're actually going to have more and more of these coming, so I can't claim the size at this moment, but as we're moving forward with more microcontroller offerings, I think from a manufacturing standpoint, doing chip scale package is not a concern, and we actually see a lot of customer interest about smaller and smaller packages moving forward. So now let me show you something new, which if you follow our microcontroller offerings, you probably haven't heard about this, which is the LPC11100. Again, I said earlier, we plan to announce this before Christmas. And what we're going to do about it, so you saw all the cool stuff happening in the LPC1100. It was a Cortex-M0 based microcontroller target for 8-bit applications. Well, what about stretching and making it bigger, adding more peripherals, adding more flash? So that's exactly what we're doing, because that's what our customers want. So we're going to increase the flash size up to 128 and offering 512 byte of erase sector. We're going to add a DMA, a CRC, and it's really cool about the CRC, which I'm going to talk about in the next few slides. And also we have 2 comparators, basically adding more peripherals, right? There's a list of things that customer can do. We really thought about this from the ground up, what intuitive things the customer can do for each of the peripherals. Well, so let me talk about the CRC, right? So we're going to support some of the common polynomials that people use in the industry. This is actually supporting DMA back transfer directly. So what's cool about the CRC? Why people need the CRC? We actually found out we saw a lot of the Cortex-M0 applications in industrial space. So customers are always concerned about noisy environment. When they get the data is not a good data, or they have to do some sort of data manipulation, sortings, and that really drains the CPU power. So once you have the CRC, you actually can do data integrity check with the DMA without the CPU intervention. So that's what we think is really cool about it. You actually transfer data from the outside to your memory space without having the CPU to do a lot of data filtering. And the other thing, let me talk about the comparator, right? So if you look at the simple diagram of this comparator, it's just not a basic comparator. We have the analog domain on the left, and then you have the digital domain on the right. So it actually can do 16 channels of input with either the positive edge or the negative edge. And the cool thing about this comparator also is you can do relaxation oscillator as a timer. And the output of the comparator is actually hooked up with the internal two 16-bit timers. So you actually, when you trigger an event, you can actually use it as a tick counter, which is another cool thing about this. So, you know, nothing fancy about a comparator, but I'm just trying to show, like, there's little things here and there we thought about it from the ground up, how a customer would use the part. So if you're interested, when the part announced, check out the user manual. There are a lot of cool things that's hidden inside. So here comes the meat of my presentation, right? I said, I want to talk about 2011. What's going to happen in 2011? What are the cool things we're going to integrate? I want to talk about 5 things in general, and namely their power profile, EEPROM integration, CAN, USB, and ROM libraries. And all this stuff we already have in our libraries. We just cool engineers and cool marketing come together and talk about what customer needs and how we're going to make a combo out of it that really sells into the market. So let's talk about power profiles. But really the target is optimizing the system power consumption. We already talked about all the graphs on the left-hand side. The LPC111L was industry's lowest active current. Now we're going to introduce a concept of power management through API. That's basically what it is. And the cool thing about it is you can optimize internal power, for example, flash operation, using a simple API call. And you can change different power profiles or settings dynamically in real time. So literally you have a routine that's called set power. You call one of these APIs once you start from default. And you get the job done in real time. And the beauty about this is, think about a lot of customers said, well, power management it's a very niche and unique thing. We have to have a very smart firmware engineer sitting there and tune that for a few days to make it beautiful. But cool thing about this, you don't have to do so much coding anymore. You tell the microcontroller saying, this is what I want to do, and the CPU will manage the power consumption of the system automatically. So CPU performance is where things you want to say, I just want to get the task done as fast as possible. I don't care about power consumption because I have a time limited window. So when that happens, of course, we can boost the performance by up to 30% without increasing the clock cycle. Okay, so for example, the CPU clock cycle is running 50 megahertz. We can boost the efficiency of the CPU by 30%. Oh. And of course, in the lowest active power mode, well, when do you need that? Well, in that case, it's typically say your CPU is running in the back, kind of doing some simple data communication. When your serial data come in, do some stuff. But in general, you want the system to have a power down mode. You don't care about how much time it takes to finish the task. In that case, if you compare with the default mode today, you actually save about up to 30% of power. So that's the cool thing about it, right?
And you do this by API call?
Yeah, that's the beauty of it. So you don't have to, again, you don't have to go in there and, being an engineer, I know sometimes it's really painful when your boss watch your shoulder and say, get the power down by another 20%. You just call the CPI call and say, hey, well, trust my hands to the NXP optimization. The next thing about CAN, right? So CAN integration. So we have a gentleman here asking me about this CAN integration. Do we have it today? Yes. So ROM integration is a very interesting concept. We actually put this ROM into our microcontroller, and our goal is we're going to have 3 levels of applications. Level 1 is very simple, either ISP, IAP, or in-system programming. So we're going to support UART, CAN, open, USB, anything that transferring data to the flash, we're going to support that. And of course, we're going to offer the code protection. We offer 3 levels, 1, 2, 3. Next level though is driver stack. Already mentioned some of the cool things is we're going to store things like HID driver in the chip. So we actually going to sell you a true 32K of flash or 128K flash without letting our customer to read the driver or taking up the code space. So that's actually a cool thing about it. And then of course the power API I mentioned is going to store in the ROM. So just to summarize my my discussion, this is the agenda presented to you today. So again, NXP is 100% ARM forecast. We're the only vendor who has the Cortex-M0, M3, M4, every single core offerings in our microcontroller families. We have the very cool 1100. We're going to bring down the lowest active current further to be the industry's leader. We're going to increase our peripheral and the flash offering in the upcoming LPC111x to fulfill the customer's demand. And we're going to have even more integrations moving forward in 2011.